Your course evaluation, you should have gotten an email about this, I hope. They opened yesterday. So for all of your courses, please, please, please do your course evaluations. I appreciate it. I take your feedback very seriously. Any comments that you make, they're very helpful to me. So please do that for all of your courses. So it's open now, and it's open usually until the Sunday before finals week starts. So basically this week and next week. So please take a few minutes to do your course evaluations. Extremely, extremely helpful. No one sees the results until well after the semester's over. It's all anonymous. There's no way for me to figure out who said what, or anyone else to figure out who said what for that matter. So it's all completely anonymous. So please do that. Okay, any questions about finite difference methods? Taylor series. As you'll see today, it turns out they're not actually that difficult to apply. They're quite easy to apply, actually. And as I said on Thursday, it's probably one of the harder lectures because it's Taylor series flying all over the place. But once you derive those Taylor series approximations, they're very straightforward to actually use. So we'll show you how to do that today. So for the remainder of the semester, just have 2 more chapters. The first is on finite difference methods for boundary value problems. And then there's a chapter on finite difference methods for initial value problems. So there are fundamentally different types of equations, different types of problems, and we'll talk about how to apply these finite difference methods to both. We're going to start off in both cases with ordinary differential equations. So this will be very similar to the kinds of things that you would have solved in Math 252, but we'll be looking at more interesting engineering motivated examples. And then we'll extend the methods to PDEs as well. And we'll do the same thing for initial value problems. Start off with ODEs and then look at PDEs. All right, so we're going to look at boundary value problems, which, as the name suggests, means that you need to have values, well, on the boundaries. Dun, 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 dun. So these are ordinary differential equations, but we need to have boundary values on the bounding values of the problem. If it's a ordinary differential equation, then it's one-dimensional. So that means on the left and the right side of the domain, you need to have boundary conditions. For partial differential equations, we'll have multiple independent variables. It could be x and t, it could be x and y, it could be x, y, and t, it could be x, all kinds of different combinations. So we'll talk about how those work as well. Haven't had any Dilbert cartoons for a little while. So this is kind of a typical coder. Yay, I have another full day of doing nothing but rearranging zeros and ones, which means coding. So back in the good old, what's actually happening on a computer is there's just switches, 0 and 1. So everything that you tell the computer to do is really getting boiled down to just zeros and ones. In fact, I just saw a really interesting illustration of this. There's a British guy, Steve Mould, who does YouTube videos about science and various things. And he has one that shows using water with tiny little tanks, water distribution, how you can build basically addition. So you can add any numbers and it shows visually how the computer is doing it with zeros and ones. It's actually very interesting. Anyway, okay, so rearranging zeros and ones. Of course, many people would read that and say, well, that's, what could be worse than that? But for us geeks and coders, that's a good day. You know it will be a good day when there is no human interaction on the schedule. Meanwhile, one of your coworkers walks up behind you and says, how's your day going? And that, of course, ruins the whole mood. Well, it started good. Notice the poor English there. And if you didn't notice the poor English, then you are one of us. All right, so we're going to talk about a specific application and get the ordinary differential equation that governs it, because it's always much more interesting to talk about and consider actual physical applications than it is just to write mathematical equations and manipulate them. So we're going to look at the extended fin problem. I'll draw this in a second. So it's heat conduction, so heat moving through a solid in this extended fin. For example, if you look at poorly designed computer chips, I won't say from which manufacturers, but for poorly designed computer chips, you'll often have the actual chip, which is very small, but then a lot of times it has this kind of casing on it. It has this, it's in something. You're like, well, I thought chips were tiny. Well, usually that's some sort of cooling mechanism. So often they will have these extended fins sticking up off the chip, and they're meant to draw heat away from the hot chip and have it convect away. So you have loud fans blowing in your poorly designed computer, blowing across the fins to cool the chip. So that might be one type of application that you would be thinking about using this for. And so we're going to use this as a way to think about the numerical solution procedure. Remember the three-step numerical solution procedure. So we'll walk through those 3 steps again. And it will help us to identify and think about how to resolve some of the issues that come up in finite difference methods in a particular setting. All right, so let's draw an extended fin. It could have a variable geometry. So x will be along the length of the fin. X equals L, x equals 0 is the base. X equals L is the tip of the fin. And then that's mounted on your chip, for example. And that is what's being cooled. So that this surface, we'll call it T sub B for base. So that's the temperature of the base at X is equal to 0. And then the idea is you have a highly conductive material in the fin. So it pulls the heat away from the base, which is your chip. And then you could, for example, blow air across this, or sometimes computers even use a fluid to cool it. And this fluid will have some temperature, T infinity, and some convective heat transfer coefficient, H. The material itself of the fin has a heat conductivity, K, and so on. All right, so that's the idea. Those are the parameters that we'll be using. Okay. So step 1 of the numerical solution procedure is to apply any physical laws and any additional assumptions or approximations that make sense for this problem. So the physical law that governs this is conservation of energy. So we're going to apply that. I'm actually not going to do the derivation. I'm just going to tell you what the assumptions and physical laws are. So conservation of energy, which means obviously if you take a sliver of this fin, whatever energy is coming in has to equal the energy going out. Heat going in has to equal the heat going out someplace. We're going to assume that the fin is one-dimensional. So in other words, it's only a function of x. And you think about, okay, so anytime, of course, someone says, well, let's make this assumption, you should stop and think, is that a good assumption? Does that assumption make sense? Is it an appropriate assumption in my engineering judgment? And so you can think about different shapes. You know, this could be short and stubby, right? It could be long and slender, like I've drawn it. If it's short and stubby, then saying it's only a function of the length x, distance from the base x, is probably not a good assumption. But if it's a long, slender one, then probably that's okay. If the area, cross-sectional area, is not changing too rapidly along the length, then that's maybe an okay assumption. So it depends. It might be a good assumption, might be a lousy assumption. We're also going to assume that the convective heat transfer coefficient, that's this H here, we're going to assume that that's a constant along the length of the fin. That's almost always the assumption that it's made, and it's almost always a terrible assumption. So, but yeah, we're kind of stuck with it. So H is basically, well, let me say it this way. What goes into determining H? A whole host of things. It depends on the shape, depends on the flow of the air or the liquid or whatever it is that's doing the cooling. It depends on the properties of that fluid. So H encompasses a lot of different information. And if you look in books, look online, you'll find all kinds of correlations, experimental correlations for H in various situations. You won't find one for exactly this geometry. If it's tapered, you will find one for a circular cylinder, which has the same cross-sectional area, but that won't account for the fact that it's stuck on a wall over here. But we're just going to push all that under the proverbial rug. We're just going to say, we don't care. We're going to use an average H. So again, this is almost always the case out of necessity, but it's almost always a terrible assumption. But anyway, that's what we're going to do. All right, so conservation of energy. Heat transfer is only a function of x, so one-dimensional, and convective heat transfer coefficient is a constant. When you do all that, put all those ingredients in to the bowl, stir it up and cook it, out comes this equation. You'll find this equation in most any undergraduate heat transfer book. So mine is in Crepier and DeWitt, and that was a classic for many years. I don't know what you guys use. This is MMAE 323. You probably haven't taken it yet. So in any case, this is a very common equation. You'll find it in any of those books. You'll see the derivation of it. Okay, so first of all, let's just define our terms. So we have capital T, that's the temperature. So it's a function of x. So that's the temperature as you go from the base at x is equal to 0 to the tip at x is equal to L. So that's the temperature along the length of the fin. A sub C is also a function of x, and that is the cross-sectional area. Well, it could be a function of x anyway. That's the cross-sectional area along the length. So if it's a constant cross-sectional area fin, then it's just a number, in which case we need to say dA dx, that's going to be 0. But if it is a variable cross-sectional area fin, then that'll be a function of x, and you can see it in this coefficient here. A sub s is the cumulative surface area from the base. So even if it's a constant cross-sectional fin, the surface area is going to increase from 0 at the base to whatever it is maximum, because it's the cumulative surface area from the base. Okay, so these are all based on the geometry of the fin. H, we've discussed already, that's the convective heat transfer coefficient. That takes into account all of these various effects that influence how the heat is convected away from or out of the fin. And then thermal conductivity, K, that is a property of the fin material itself. So that's something, you choose a highly conductive, steel or copper or something like that. And then you get the value K out of a book or specifications for that material. Okay, and then you have this equation. It's a second order, because the highest derivative is 2. It's linear, even though it kind of looks like a complicated equation. It's linear in the dependent variable t, because we just have a d squared t dx squared, dt dx, and then a t term. All of this stuff makes it a variable coefficient, ODE, but it's still second order and linear. So it's a second order linear variable coefficient equation for the temperature as a function of x, given all of these various properties of the system. Great. We're going to simplify the equation down a little bit. So we're going to define a new variable u as t minus t infinity. So I'm just going to subtract off the ambient temperature of the fluid that's doing the cooling. And that'll just make things a little bit more convenient. You notice there's a t minus t infinity here, so that's just going to become a u. And dt dx, that's just going to become a du dx, d squared t dx squared, that's just going to become a d squared u dx squared as well, because this is just a constant. And so what we'll end up with is a slightly simplified version of the same equation. So I've written in a more generic fashion here as a second order linear variable coefficient non-homogeneous equation. I wrote it as non-homogeneous with an h on the right-hand side. The f, it could be a function of x. The g could be a function of x. And for our situation, here they are. So the f of x, that's just this coefficient right here, 1 over ac, dac, dx. That's here. And then g is the coefficient on u, which is this coefficient right here, minus 1 over ac, h over k, das, dx. So I'll just lump all those things together. And so now we can more readily see the form of the ordinary differential equation. In this case, h is 0, in which case we say that the equation is homogeneous, which is always just our fancy way of saying something is equal to 0. Boundary conditions. So we have a second order ordinary differential equation. So we need 2 boundary conditions, one at each end, at the base and at the tip. So at the base, at x is equal to 0, the temperature is equal to the base temperature, but we subtract off the T infinity, so that's U. So U is U sub B for U base, which is TB minus T infinity. Likewise, for now, this is a terrible boundary condition because it's not physical. I'll talk about that in a moment. But for now, we're just going to say that we also know the tip temperature at x is equal to L. So once again, U is U sub L, which is T sub L minus T infinity. So we're going to pretend that we know the tip temperature, subtract off the ambient temperature T infinity, and then that's our boundary condition for U. These are called Dirichlet, not Dirichlet. Dirichlet, it's French, so of course it's beautiful and rolls off the tongue. So this is called a Dirichlet boundary condition, or some people just call it a fixed or a specified boundary condition. The point is we're specifying the temperature at the base as well as the temperature at the tip. Now, it's a terrible boundary condition at the tip because I don't know what the temperature is going to be. It all depends on what happens, right? So the heat is coming off of the hot chip. So that's TB. I know what TB is. But how do I know how much heat is coming out and what the temperature at the tip is going to be? Of course, that's partly what I'm solving for. So we'll address that shortly. But for now, just to keep things simple, we're going to pretend like we know the temperature at the tip. All right, so that is step 1 of the numerical solution procedure. We have our governing equation, 9.2, and we have our boundary conditions, 9.3. So together, that is our system of differential equations that we want to solve. That is the mathematical model. That is the result of step 1 of the numerical solution procedure. Step 2, of course, is then to discretize. So we discretize the domain and we discretize the equation itself. So let's start with the domain. So our domain, it's a boundary value problem from x is equal to 0 to x is equal to L. And here's how we're going to discretize it. We're going to take and divide it up into capital I equal subintervals along the length of the fin. So in other words, each little subinterval is going to be of length L over capital I, the length over the number of intervals. The way we'll label them is as follows. We'll start with I is equal to 1 at the left-hand side, and then just go across 2, 3, and then a generic I minus 1 to the left, I plus 1 to the right. The point just inside the right boundary would be capital I, and at the right boundary will be capital I plus 1. So there are capital I intervals and capital I plus 1 points. There's always one more point than there is interval. Each of the intervals is delta x long. So in terms of x, this I point, that's x sub I, The one to the left is x sub I minus 1. The one to the right is x sub I plus 1. Okay, so that's how we're going to number the points discretized across the domain. So we call this a grid. We call it a mesh. Those are the terms we use interchangeably to refer to how we discretize the domain itself. We're also going to use a bit of shorthand here. We've used something similar to this before. So when I say f sub I, what I really mean is f evaluated at x sub I. Same thing with g, same thing with h, same thing with u. So u sub I really means u evaluated at x sub I. So it's just a shorthand to indicate the location at which we have the value of f, g, h, or u. Now, I know the boundary conditions, so I actually know the temperature here and here at the two ends. That's UB on the left and UL on the right. So I don't need to calculate these. So the unknowns are all the interior values of I, the interior points. So the unknowns correspond to little I from 2 to capital I. Because I know at 1 and I know at capital I plus 1. Now, if I had something other than Dirichlet fixed boundary condition on one of those sides, which we will in a moment, then that will change. But for now, I know the value of t at the end. I know the value of u at the ends. Therefore, it's only in the interior values, interior points at which I'm solving for u, the unknowns. So here's my equation 9.2. Just repeated it here. And then I have my Dirichlet boundary conditions repeated here. All right. So now we need to discretize the equation itself. So we've discretized the domain, and now we're going to discretize the equation. So our continuous differential equation with these continuous derivatives in it is going to get transformed magically into a system of linear algebraic equations. Remember, that's the outcome of step 2. Input to step 2 is the governing equation. The output to step 2 is a system of linear algebra equations to solve. So that's what we're aiming for. Okay, so now we're going to, as I said, discretize our differential equation. Well, I have first derivatives here. I have a du dx. I have second derivatives, d squared u dx squared. So this is a finite difference method. So let's use finite difference approximations like so. The standard is to use second order approximations, second order accurate central difference approximations. There are situations, as we'll see, where that's not possible or not advisable or whatever. But in general, that's kind of the default. That's the standard. So second order accurate central differences. We like second order accurate central differences because it usually only involves the point itself, I, the point to the right, I plus 1, and the point to the left, I minus 1. So it only involves 3 unknowns, which, as you'll see, will lead to a tridiagonal system of equations. So I'm getting ahead of myself. So the first derivative, du dx, we're going to use a second order accurate central difference approximation to, well, approximate it. So that's ui plus 1 minus ui minus 1 over 2 delta x. We derived that last time using Taylor series. We don't actually include this term, the order delta x squared term. I just have it there to remind us that it is indeed second order accurate, but we don't actually include it in the finite differencing process. Similarly, for the second order derivative, d squared u dx squared, you go look, second order accurate central difference, and this is what you'll find. This is what we derived on Thursday. ui plus 1 minus 2 ui plus ui minus 1 over the square of delta x. Once again, that is second order accurate. Once again, we don't include this term in the actual calculation. We're just writing it to emphasize the second order accuracy of the approximations. Great. So all I'm going to do is replace the first derivative with this and the second derivative with this in our governing equation right here. So the second derivative is right here. That's ui plus 1 minus 2 ui plus ui minus 1. You'll see this so many times, it'll become ingrained in your brain and you'll never be the same again. Then plus f times du dx. And du dx is this, ui plus 1 minus ui minus 1 over 2 delta x, which you now see here. Then gi times ui is equal to hi. So we were approximating the governing differential equation at a generic I point, xi point in the grid. We have a whole bunch of these xi points, I going from 2 to capital I. Do they actually have the air conditioner on in here? This is awesome. I expected today to just come in and just have sweat just running down my face behind this mask. They actually turn on the AC. Oh my. I could go on all night now. Awesome. No? Okay. So we're applying the equation at a generic xi, and I is going to be 2, 3, 4, 5, all the way to capital I. So we're going to have a whole bunch of these equations. That's my system of linear algebraic equations, as you'll see in a moment. All right, so differential equation, substitute in the finite difference approximations, and that leaves us here. Now what we want to do is we want to gather all the terms together, because I have a ui plus 1 here, ui plus 1 there, minus 1, minus 1. So I want to gather all the terms together. Here's a ui, here's a ui. So I want to gather all the terms together and clean things up. And the way we write our finite difference equations is to put all the unknowns on the left and all the knowns on the right. Everything that I don't know, if there's a term that there's something I don't know in it, I put it on the right, on the left, excuse me. And if I know everything in each term, in those terms, I put it on the right. So that's what we're going to do. I'm also going to multiply through by delta x squared. I'll talk about why that is in a second, but let's just walk through this. So the ui minus 1 terms. Well, here's a ui minus 1. That's a 1 over delta x squared. Here's a ui minus 1. That's a minus f over 2 delta x. And then, as I said, I multiplied through by delta x squared. So that gives me a coefficient a, which is 1 minus a half delta x fi. So that's just all the stuff times ui minus 1. Then all this stuff times ui is b, minus 2 plus delta x squared times gi. And again, I have a ui here and a ui here. So everything times ui goes into my b. Likewise, for ui plus 1, everything times ui plus 1 goes into the c. And you'll notice a nice symmetry. The a and the c are the same. The only difference is the minus sign here. So c is 1 plus a half delta x fi. Then the right-hand side, d. So that's all the stuff that's known. That's delta x squared hi. Now, in our particular situation, hi is 0. And I know fi and gi, but we're just using them generically for now. We'll put those in later on. Okay, does everybody follow what we're doing? Pretty straightforward, just a little bit of algebra. This is our difference equation. So once we apply the finite difference approximation, put everything in, and then gather the terms together, put the known stuff on the left and the unknown stuff on the right, that is our difference equation. That's the starting point. That's the ending point for step 2 and the starting point for step 3, as you will see. Okay, what about boundary conditions? Well, I know that U1 is UB. U1, I is equal to 1, is the left boundary. That's the base of the fin. Likewise, at the tip, that's xi plus 1, capital I plus 1. That is known, that's U sub L. So from the boundary conditions, I know U1, and I know ui plus 1. So if I were to apply my finite difference equation at I is equal to 2, so I take 9.4 and I apply it at I is equal to 2. So what I get is the following. I get A2U1 plus B2U2 plus C2U3 is equal to D2. Again, that's just this with I is equal to 2. Gives me this. But then I stop and I look and I say, wait, I know what U1 is. U1 is UB. So if I know that, I can take that over to the right-hand side. Remember, unknowns on the left, knowns on the right. So then I have B2U2 plus C2U3 is equal to D2 minus A2UB. So this is now my first equation corresponding to I is equal to 2. So it's started off with the difference equation, and all I did was I said, okay, what do I know about this equation? Because it's at the left boundary. I know the boundary condition at the left, so I should be able to simplify it. Same thing on the right. So the last equation corresponds to little I as big I. So when I put in little I as big I to my difference equation here, I get, and all these I's are capital, I have AI UI minus 1 plus BI UI plus CI UI plus 1 is equal to DI. But again, I remember, wait, I know what UI plus 1 is. That's the boundary condition UL. So if I replace UI plus 1 with UL, that then goes to the right-hand side because I now know that term, and I get this. So in other words, I'm just taking into account the fact that for I is equal to 2, the first equation, I is equal to capital I, the last equation, because they're going to include the first and last point, which I know from the boundary conditions, I'm just going to consider them and see what they are, because they're a little different. All the others are going to be the same. From 3 to capital I minus 1 are all going to be the same. So here's what it looks like. So I'll come back to this explanation at the top, but here's what it looks like. So the first equation is for I is equal to 2. And if I look at that equation, it has B2 times U2 plus C2 times U3 is equal to D2 minus A2UB. That better be the same. Yep, right there. Equation 9.7. Then the last equation for I is equal to capital I, that is now AI times UI minus 1 plus BI times UI is equal to DI minus CI UL. And that better be this one. And it is. All of the other equations for 3, 4, and then this is capital I minus 1. For all of those interior equations, it's just A3 times U2 B plus B3 times U3 plus C3 times U4 is equal to D3. And then everything just shifts over. A4 times U3, B4, U4, C4, U5 is equal to D4. That's, I'm just writing down all of those equations in matrix form. That's all we're doing. All right, now let's come back and think about this. So how many equations do we have? Well, I have as many equations as there are unknowns, which is capital I minus 1. There's capital I plus 1 points, but I know the left boundary point, I know the right boundary point, so that's 2 of them. So if I have capital I plus 1 points, 2 of them are known, that leaves capital I minus 1 unknowns, and I have 1 equation for each of those. So I have a big system of equations, capital I minus 1 equations for capital I minus 1 unknowns. Great, that all makes sense. I've highlighted in red the adjusted terms on the right-hand side. You'll notice all of these from 3 to capital I minus 1 are just the corresponding D's, just from my generic finite difference equation. But the first one, corresponding to I is equal to 2. The last one, corresponding to I is equal to capital I, those have been adjusted with the known stuff on the right. Of course, I look at that and I recognize that from much earlier in the semester, that's a tridiagonal system of equations. We love tridiagonal systems of equations because we love the Thomas algorithm that we use to solve it. It's very efficient, it's very fast, it's simple, and it's direct. So all of those things make it wonderful to solve. So that is step 3. Step 3 is to solve the system of linear algebraic equations. And in this case, it is a very simple system. It's tridiagonal, so it's easy to solve using the Thomas algorithm, which again, we talked about way back in chapter 2-ish. Couple comments here. As I've mentioned several times now, the custom is to write these finite difference equations with the unknowns on the left and the knowns on the right. So every time I write them out, I do all the algebra, and then the last step is I put anything that's known on the right, leave anything that's unknown on the left. Now let's talk about this delta x squared. Remember, I multiplied through by delta x squared. Let's think about why that was. So here is the equation after I put in the second order accurate central difference approximations, the finite difference approximations. And you'll notice I have divide by delta x squared, divide by delta x here. Now, delta x is small, right? I have lots of points in general, and so delta x is small. So if I square a small number, it gets even smaller. If I divide by that small number, I have a big coefficient, right? So I don't like that. I'd like to give my computer A's, B's, C's, and D's that are order 1. I don't want them to get really big. I don't want them to get really small. So simply by multiplying through by delta x squared in this equation, we'll make these coefficients order 1, as you see right here. It's literally order 1, order 1, order 1. And then you're adding and subtracting small values. So that's nice. The computer's happy, and I don't have to worry about, is it going to handle those small numbers or large numbers okay, because they're all just, well, they're order 1. So it's not necessary mathematically. I haven't changed anything mathematically. However, from a computational point of view, it makes sense, and it's certainly very easy to do. All right, so that takes care of that. Now, the other thing that we talked about way back in chapter 2 is how do we know that we're going to get a solution to our system of equations. So we talked about conditioning of matrices. We talked about conditioned numbers. We did, remember, the Hilbert matrix, which is horribly ill-conditioned, lots of round-off errors. But the easy check that we gave you at the time was we said, well, the easiest thing to look at, because I can tell by inspection, I don't have to calculate any eigenvalues and so forth, is just to check to be sure it's diagonally dominant. So in this case, diagonal dominance means that the main diagonal coefficients, whoops, kind of missed there. In other words, the B's have to be bigger than the sums of the absolute values of the A's and the C's. If that's true, then it's diagonally dominant, and you can prove that if it's diagonally dominant, then it will have nice properties in terms of actually getting its solution. You don't have to worry about round-off errors doing horrible things to you, and so forth. If you ever do a finite difference problem and you get your finite difference equations and you check it, as you dutifully will, to be sure it's diagonally dominant. If it is not diagonally dominant, then you need to go back to the drawing board and come up with a different approximation. You need to go back to step 2. If you don't do step 2 properly, then step 3 won't work. So if I see that it's not diagonally dominant, in which case I expect round-off errors to give me problems because it's poorly conditioned, then that means I need to rewind back to step 2 and rethink how I did step 2 and come up with a better algorithm, a better method. Okay, but we're fine here. We can actually check. It's not a bad idea to check, Castle. Let's do it. So here's our A, and here's our C and our B. Now notice, if the F and the G are 0, then it's just 1 minus 2, 1. 1 plus 1, last time I checked, is 2. So that would be weakly diagonally dominant. It's just big enough to balance with the B. With these terms, it is diagonally dominant. Not hugely, but it is at least diagonally dominant. So that's good. All right, so we're good on that front. So check. Okay. Now let's think about this. Let's rethink this boundary condition at the tip. So we assumed we knew the temperature. Obviously, we don't know the temperature. Physically, that doesn't make any sense whatsoever. We did it just to keep things simple, so we didn't have to worry about boundary conditions, at least, you know, mucking up the works here and getting our difference equations. So now let's take a look at a more physically appropriate boundary condition. So this will be a convection boundary condition, which is what we have, right? So we have our fin sticking out. The heat gets conducted through the fin. Some of it gets convected away along the length of the fin. And at the very tip, if the temperature is higher than T infinity, then there will be some convection from the tip as well. So the way that that is accounted for is by basically balancing the energy, the heat coming out of the tip and into the fluid. That's according to Fourier's law. This is Fourier's law here on the left. Fourier's law, another smart French guy. So what it says is the heat conducting out of the tip, which is the left side of the equation, minus k dt dx. So whenever you see a dt dx where it's the temperature being differentiated, that represents a flux. That's a heat flux. That's how much heat is fluxing out of the tip. It's conducting out of the tip, minus k dt dx. That is all being convected away. Whenever you see an H, you know it has something to do with convection because that's our convective heat transfer coefficient. So the H times the difference in temperature gives us how much convection is occurring. So the conduction out the tip is equal to the convection into the fluid from the tip. So this is a more appropriate boundary condition to apply at x is equal to L. As you'll see, it's called a Robin condition as opposed to a Dirichlet condition, or some people call it a mixed condition for reasons that you'll see in a moment. We apply our change of variables again. So subtract T infinity off of T to get U of X. So on the left, you have dt dx, that just becomes du dx. And then the T minus T infinity here, well, of course, that just becomes a U. So minus K times du dx at the tip is equal to H times the U at the tip. So you'll notice before we had U being specified at the tip, so U is equal to something. Now we have a linear combination of U and the first derivative du dx being specified. So that is called a Robin condition or a mixed condition. And that represents, again, convection at the tip. So that's a much more physically relevant, physically motivated boundary condition. Generically, we're going to express it this way. So we're going to say at x is equal to L, we have a linear combination of U and du dx is known. So we're going to put a P coefficient on the U, a Q coefficient on du dx, and an R on the right-hand side, just generically to take care of this boundary condition as well as any other Robin or mixed boundary condition that might arise. In our case, the P is H, because that's what's multiplied by the U. Our Q is K, because that's what's multiplied by the du dx. And the R is equal to 0, because there is no R on the right-hand side. All right. So the way that you would specify this is you would input the P, the Q, and the R. Those would be known as they are here, H, K, and 0. You would input those three values, and that would define the boundary condition that's being enforced at the tip. Okay, so this is a little bit more involved now. So we have to think about, okay, now I no longer know the temperature at the tip. So that's U at capital I plus 1. So I need to calculate it. How am I going to calculate it? Well, to start with, let's write down the let's write down the governing equation, the difference equation, at the boundary. And just see what happens. Just see what it gives us. So I'm going to write it at little I is capital I plus 1. So this is our difference equation 9,4. So here it is. Same thing as we had before, but now written at little I is capital I plus 1. Before we wrote it at little I is capital I. Now it's capital I plus 1, right at the boundary. And you look at it, the first term AI plus 1 times UI. Okay, that's fine. UI plus 1, UI plus 1. All right, that's okay. The UI plus 1, that's the boundary value. But then the CI plus 1, UI plus 2. Oh my, wait, what's that? So here, if I zoom in on the right boundary at x is equal to L, the This is capital I, this is capital I plus 1. So this is saying I need the point capital I plus 2 out here, which of course isn't even in the domain. I don't know that point. I don't care about that point. I don't want that point. That point doesn't exist. Some people call it a ghost point. It's a little ghost sitting outside the domain. So I've highlighted it in red, ui plus 2, and we need to eliminate it. We need to get rid of it because it doesn't exist. Well, how do we do that? Well, this came from the governing equation itself. Let's look at the boundary condition. Let's see if we can use the boundary condition 9,9 in order to determine what ui plus 2 is, so we can use that to substitute in here and eliminate this. That's exactly what's going to happen. So I'm going to take 9.9. I'm going to finite difference it. You see the du dx in here. So use a second order accurate central difference approximation for that. And then I'll see if I can use it to eliminate this ui plus 2. All right, so here's the p ui plus 1 plus q. Then we had du dx at I capital I plus 1. So that is ui plus 2 minus ui over 2 delta x. That's just a second order accurate central difference approximation for that first derivative. And that's equal to r. And you notice, there's a ui plus 2 in there. So if I just solve this for ui plus 2, the ghost point, the point outside the domain, then I could substitute that into the previous equation and eliminate the ui plus 2. So that's exactly what we're going to do. So I'm going to solve this equation from the boundary condition for ui plus 2. Easy peasy. And I get this. And then I substitute it into here for ui plus 2. And then I'll no longer have a ui plus 2 because you'll notice once the ui plus 2 has been eliminated, it just gives me more ui's and ui plus 1s, which are fine because those are inside my domain. I do that, I collect all the terms together, and I get this. This looks messy, but all it is I have a new coefficient times the ui, a new coefficient times the ui plus 1, and a new right-hand side. So this is a new ai plus 1. This is a new bi plus 1. And this is a new di plus 1. And you'll notice it has the old ones in it. The old a's, b's, and d's. So these are assignment statements like in a computer programming kind of context, not like in a math context. So I replace the old ai plus 1 with this. I replace the old bi plus 1 with this, the old di plus 1 with this. So those adjustments are made to the the last equation, because this is the last equation applied at capital I plus 1. And that's it. It's a little tedious, a little bit of tedious algebra, but it's not difficult to actually do. So now this becomes my last equation in my system of linear algebraic equations. It still fits within the tridiagonal system framework that we had previously, so we're good to go. So now I do have one more unknown, because I have little I being capital I plus 1 as an additional unknown. So I actually have capital I unknowns. Before we had capital I minus 1 unknowns, but now we have one more unknown, so it's capital I unknowns. We only know one of the points instead of 2. Now, the Robin boundary condition where we had P times U plus Q times du dx is equal to R. If you set the P is equal to 0, then you get what's called a Neumann boundary condition. So a Neumann boundary condition is where you have, this is Neumann, this is where you have du dx being specified. So I guess it would be R over Q. So We could have u being specified, that's Dirichlet. We could have du dx being specified, that's Neumann. Or we could have a linear combination of the two being specified, that's Robin. So 3 types of boundary conditions. Okay, any questions so far? It's very tedious, not difficult. That's kind of the name of the game when it comes to finite difference approximations for differential equations. When you go to PDEs, it's just gonna be more of the same, more tedious algebra, but no more difficult. All right, now one thing you might wanna know is what is the heat flux out of the base of the fin? How much heat is being drawn out by the presence of the fins in order to cool the hot running computer chip, poorly designed hot running computer chip. So to calculate the heat flux, use Fourier's law again. And it says that the heat flux, Q, is minus K times the area, the cross-sectional area. So that in this case is at x equal to 0 because we're calculating this at the base, times the gradient, dt dx, the flux of the temperature. So minus K times A, dt dx. In terms of u, it's just minus K times A sub c times du dx. So we need to approximate the first derivative of u with respect to x at the base, x is equal to 0, in order to approximate the amount of heat fluxing out of the base. So I have to now use a forward difference. I can't use a central difference at the base because that would involve a point outside the domain, as we just saw. So I now have to use a forward difference. And I could use different approximations. We've seen 3 of them. I have a first order accurate forward difference approximation right here, u2 minus u1 over delta x, which is first order accurate. We had a second order accurate version, which was this one, minus 3 u1, excuse me, plus 4 u2 plus minus u3 over, I'm just so excited because the Bulls won last night. They actually won, finally. Oh, they're just driving me crazy this year. Okay, oh, like every year. I don't know what the why I should expect any different. Anyway, so then this is a second order accurate forward difference. It only involves the point and 2 points to the right, 1, 2, and 3. We could go even farther. We actually did derive a third order accurate first derivative. We didn't do it in class, but it was in the notes. It was grayed out. So that would require, as you can see, 1, 2, 3, 4 points in order to approximate the first derivative using a forward difference approximation. So in any case, we could, obviously you would expect the third order to be better than the second order, which would be better than the first order. Doing so, of course, requires more calculation, 2 points to 3 points to 4 points. So there's always that trade-off. All right, so that's to get the heat flux. Now, let's look at a more generic example. That was a heat conduction situation with convection. Maybe the physics confused us. So let's just look at a generic second order boundary value problem, which is what that was. But let's just look at it this generically. This will include that case, but be more generic. So a general second order boundary value problem will have second order derivatives and then some function of the independent variable x, the dependent variable u, and its first derivative. All right. F could be linear, it could be nonlinear. In our case, for the fin problem, it was linear, but it could be linear or nonlinear. Again, we have various types of boundary conditions. We have Dirichlet, where u is known at the boundaries. Neumann, where the normal derivative of u is known at the boundaries. Or Robin, where a linear combination of u and the first derivative is known at the boundaries. So any one of those 3 possibilities. And of course, you could have different ones on different sides, just as we did for the extended fin. So I could have Dirichlet and Robin on either end, as we did for the convection condition at the tip. I could have Neumann and Dirichlet. I could have any combination of these 2. So let's look at a specific example that fits in this category. D squared u dx squared plus 2 du dx plus u. Again, second order, it's linear, and now it's constant coefficient. So in fact, this one we can solve using methods for Math 252. It's a linear, second order, constant coefficient equation. It's homogeneous. So you can solve that exactly. Here is that solution. That'd be good practice for you to remind yourself how to do that. Here are the boundary conditions. These are given. At x is equal to 0, u is 1. At x equals 1, u is 0. Those are the boundary conditions. So we have the exact solution so we can compare it, but we're going to pretend like we don't know this and continue on and do this numerically. So presumably step 1's already been done to get the governing equation. That gave us 915. Then we do step 2 to discretize exactly like we just did for the extended fin case. Now the f is 2. Okay, that's the coefficient of the first derivative. G is 1. That's the coefficient of the 0th derivative term. So that's 1. And then h is 0. That's the right-hand side. All right. So we already have the setup for this. We know the FG and the H. We've already done all the hard work. We finite difference this thing. So I get my tridiagonal system, just like before. I know the A, B, C, and D coefficients. It's 1 minus a half delta XF and 1 plus a half delta XF for A and C. And then for B, it's minus 2 times delta X squared times G. But F is 2 and G is 1. So it's 1 minus delta X and 1 plus delta X for A and C. And then B is minus 2 plus delta X squared. So this is a specific version, again, of this linear ordinary differential equation. Let's use Dirichlet bound. Well, we were given Dirichlet boundary conditions on the end, so those are known. So U1 is known, it's 1, and U capital I plus 1 is known, that's 0. That's from the boundary conditions. So I do the adjustments. I've done all this before, so I'm just putting in the actual values now. So I do the adjustments on D2, and D capital I is D minus A and D. All right. You'll notice I've taken off the subscript I from A, B, C, and D because they don't depend on X. They're the same all the way across. So that simplifies things a little bit. So it's still a tridiagonal system of equations, but all the A's are the same, the B's are the same, and the D's are the same. Well, the D's are the same except for the first one. All right, solve it. So you solve your tridiagonal system of equations using your Thomas algorithm. This is for a capital I of 20. So we have 21 points, 20 intervals. That corresponds to the dots. Those are the numerical approximate values at each grid point. And there should be 21 of those dots. Starts at 1, the left boundary condition, ends at 0, the right boundary condition. It has to satisfy those, of course, because, well, they're boundary conditions. And then you have the exact solution, which is the solid line. And you can see the numerical solution agrees very, very nicely with the exact solution for this relatively boring, smooth case. But that warms my heart. Things are working properly. Here's the actual values, the numbers. I'm showing them not for all 21 points, but every other point. So I is equal to 1, 3, 5. I've taken out the even valued points. Here are the numerical values that I got from my numerical solution from tridiagonal system of equations being solved. These are the exact values from the exact solution, and this is the difference between them, the absolute error. You'll notice the errors on the two ends are 0, which makes sense because I know the value of u at the two ends, so the error should in fact be 0 there because the numerical solution and the exact solution should, and they do, match exactly. So that's good. And so for Dirichlet boundary conditions on both ends, it's typical, and that's the case here, that the maximum error occurs somewhere in the interior. It's not necessarily right at the middle, as you can see here, but it's in the interior. You can see how this is solved using built-in functions in the Python tutorial if you're interested. Now this is interesting. So this is convergence, not iterative convergence in a Gauss-Seidel sense, but this is convergence in a numerical converging solution converging to the exact solution sense. So as I increase the number of points, my solution should get more and more accurate. The value of the error should get smaller and smaller, and it does. But not only that, it should get smaller, it should converge in a predictable fashion. So remember, all of my approximations are second order accurate. So what I've included here in this column is the actual square of delta x. So as I increase the number of points, the value of delta x gets smaller. And of course, you square it, it gets even smaller yet. So it's getting smaller with each doubling of the number of points. So if I double the number of points, I'm halving the delta x, but then that's squared. So a half squared is, of course, a quarter. So it goes from 0.04 to 0.01 to 0.0025 to 0.000625. Now the maximum error, that's this value right here. So now this one's at 9, and it actually doesn't quite match with this value here. And that's because the actual maximum apparently did not occur at 9. It either occurred at 8 right here or 10 right here, numbers that aren't shown. So in any case, as I increase the number of points and therefore have, so double the number of points, and therefore have the delta x, the error goes down by a factor of 4. And it does so exactly. So if you take this number right here and divide by 4, you'll get, well, not exactly, but you'll get something very close to this. Divide that by 4, you'll get this. Divide that by 4, you'll get this. So the question is, does that all make sense? And the answer is, well, it better, otherwise I made a boo-boo. So it does make sense because, again, if I have delta x, then that means the error, which is order delta x squared, goes like a quarter, goes down by a fourth. And so that's exactly what's happening here. So each time I'm just dividing by 4 in order to get the error. So that makes sense. That illustrates this convergence process, which we talked about way long time ago. All right. Anything else important here to say, Castle? Nope, said all that. Good. Oh, words of wisdom. Castle, you're so smart. Your words of wisdom are so helpful. Okay, debugging. So I haven't beaten you over the head too much with programming in this class. I try to, on each problem set, have one sort of kind of programming problem on there. I'm sure, I haven't actually looked at this, but I'm sure some of you have just not done those out of some religious opposition to coding. I don't know. And maybe you'll do fine in the class, maybe you won't, I don't know, we'll see. But in any case, so for those of you, which hopefully is all of you, that are doing the coding, one thing that you learn, hopefully, are debugging strategies. And I'm not giving probably enough coding in this class to really learn these strategies, but let me just give you a couple of pointers when it comes to debugging. The first one is what not to do. So what I call the shotgun approach to debugging. So a shotgun is one bullet comes out, but in a shotgun, you have a whole bunch of little metal pellets. So this is like when you're hunting with a shotgun, it's like, well, the deer is over there somewhere. You just kind of sort of aim in that general direction, and you probably will have enough of the pellets because they spread out, enough of the pellets hit that deer that it dies and there's dinner. Sorry. Well, that's a horrible way to hunt, and it's a horrible way to debug. So the shotgun approach to debugging is, I write my code, I hit the go button, and I watch it, and it doesn't work. So then you just start just throwing stuff at the screen. You're just like, well, let me try this. Let me try that. Let me change this. Let me change that. And that's the shotgun approach. Do not, it's a waste of time. You're probably doing more harm than good when you do that. Okay, so that's what not to do. What should you do? Another thing to keep in mind, and I do this a lot, is you're always looking for where the bug is, right? Remember bugs, why we call them bugs in our code? Because it's the moth and the, in the vacuum tube. So you're looking for where the bug is. But one of the best strategies to find where the bug is to determine where the bug is not. So by a process of elimination, you can say, well, I know the bug is not in this portion of the code because I wrote that code, I tested it, and it's now a standalone module. So I trust that module. And this is an advertisement for modular programming because you can isolate and reuse code. And you can trust it. I tested it. I've convinced myself that this module of the code works correctly. So wherever the problem is, it's not there. Therefore, it has to be somewhere else. And by, in a modular way, going through and figure out where the bug is not, eventually you'll narrow down where it is. And that also goes to testing. So you test various aspects of the code. And sometimes your testing is, I'm absolutely sure that when I put this in or I do that, it's going to give me this result. So you do it 9 times out of 10, you get exactly back what you expected. Good. Check that off. The bug is not there. Sometimes there's that case where, oh, wait, that's not what I expected. Maybe there is a bug in there that my testing did not expose. But usually you're exposing where it's not, and that's helping to point you where the bug is. It's a more methodical, it requires more patience, more methodical approach, it requires more patience. It's the complete antithesis to the shotgun approach, which is just usually a big waste of time. This last comment is not so much about debugging, but it kind of is related to debugging in the sense that sometimes you'll turn in stuff that doesn't work. And normally you've been conditioned in your classes, right, that you do the best you can, you get some answer, sometimes you don't, but you get part way, you turn it in, you're like, well, okay, I'll get 50%, I'll get 75%, I get partial credit, great. One thing I actually like about coding from a pedagogical, it means teaching point of view, is that there is no partial credit. Now we may give you partial credit because you took the time to write some code, even though it doesn't work, we'll give you partial credit as far as the grade goes. But the computer itself doesn't give you partial credit. The computer doesn't say, oh, well, she tried hard. She gave it a good go. Let's give her an E for effort. You know, the code just says, no, that's wrong. And until every piece is right, it's wrong. And it gives you the wrong answer. And that's frustrating, absolutely frustrating. Believe me, I've known that frustration for many, many years. But from a pedagogical point of view, I think it's actually helpful. It's helpful to have something in your life that doesn't give partial credit. This is engineering. It's not, well, we're going to build 10 bridges and we hope 9 of them stand up. It's we're going to build 10 bridges and all 10 better stand up. So when I run my code, it better give me the right answer. And if it doesn't, I need to know that. So in any case, that's just kind of a interesting aspect of a class like this and the coding aspect of it that I think is actually quite helpful for us as engineers. Okay, we're going to stop there. We'll pick up on Thursday and extend these techniques to PDEs. Same basic approaches, same basic underlying methods, but we'll extend it to partial differential equations like Poisson equation. We've seen Gauss-Seidel method before. Now we're going to adapt it to a PDE setting. All right, so I'll see you. And I know you're all just chomping at the bit for another problem set. I know you've gone now like what, a week and a half without a problem set to do. And I know it's just killing you. I know. Be patient. I will give you one on Thursday. Your last one. Really? Oh, don't worry. It won't be bad. It'll just be full of coding. No, I'm just kidding. So yeah, that'll be the last one. Took us a while to get there, but that'll be the last one. All right, so I'll see you on Thursday. I thought we were done.